right, ladies and gentlemen, let us go over our Unit 4 review that starts on force diagrams. So what we have here to start is a bowling ball, which we've had lots of experience with. A 2 kilogram bowling ball is stationary on the floor. So we need to have a force diagram, and remember you're starting with a ball or a square. We know we have our downward force, Fg, and we have our upward force, Fn, because it's on the floor. We have F equals ma to figure out the number of the force. It is 2 kilograms for our mass, and our acceleration on Earth is 10 meters per second squared. And so our force is 20 newtons. Because remember, inside of a newton is a kilogram meter per second squared. So we need to go through and label our information. I'm going to put my congruency marks on there so that I know that they intend to be the same. It is 20 newtons of gravity, and because they're balanced, it is 20 newtons of normal force. And then we're going to go with our dealer feelers. Okay, so again, my object is going to go second, so that's the ball. And then what is pulling the ball down? It is the earth, so E. And what is holding the ball up from sinking into the earth? That is the floor. So I'm going to put F. My net force direction, net force is going to be 0, and there's no motion because there's no force. Okay. Now, question number 2, we have also that is balanced. Sorry. That's the Y. It is balanced. So the forces on the 10 kilogram box, again, I'm going to go F equals ma. My mass is 10 kilograms. Acceleration is also 10 meters per second squared. So my force on that box is 100 newtons. And what I like to do, so I don't confuse myself, is circle the object that we're talking about. And I'm doing that for one real reason, because I have a lot of people ask me, is it the man that's pulling on the box? And if you look at my circle, what's the only thing touching the box? It's the rope. So rope is providing that upward force. And we know that the upward force from a rope is force of tension. And that is going to be dealing the force is the rope, and feeling the force is the box. Okay, so it also has these buzzwords here. Constant speed. Constant speed means that it needs to go the same amount. It needs to be balanced because it has a net force is 0. And it is going to stay at a constant speed. Okay, so we have our upward force. I got a little distracted with all the other things. We also have that downward force, Fg, and that is the earth on the box. And it is 100 newtons. It's 100 newtons down and 100 newtons up. 100 minus 100 is 0. Question number 3, we have that 2 kilogram cricket ball. And again, F equals ma. You know by now that you have to write the formula to get your points. You have to show your work, as I'm doing right here. And then you have to get a proper answer. 2 times 10 is 20 newtons. Okay, so the mallet ball, or cricket ball, I should say, is 20 newtons. It is the same as what we saw up at the top, a bowling ball, very light bowling ball, very heavy cricket ball. So we have 20 newtons of gravity by the earth on the ball that is going to balance an upward force, and that ball is on the floor or on the ground. So we have Fn, and that is the floor on the ball, and there's also 20 newtons. What we don't know is how much force is being struck by the mallet going that way. You can tell it's going that way, but we don't know how much it is. So I'm just going to put a random sized vector over there. And I'm going to call that FA. And again, my object that we're looking at is the ball. And what's hitting the ball? The mallet. It is not necessarily equal. We don't know. We don't have we do not have a quantity, so we can't tell if it's equal or not. Net force direction, it's going to go, my F net, or net force, is going to be greater than 0. It is going to go to the left, so it's going to accelerate to the left because it is unbalanced. Okay, number 4. We have a couch that is 2,000 newtons. We don't even need to do a calculation here because it's already in newtons, so be careful about that. But 2,000 is a heck of a lot bigger than 20, so I'm going to make my real big vectors here. My FG is 2,000 newtons, and that is the earth on the couch. And then we also have 2,000 newtons, and that is normal force, and that is from the floor to the couch. And then I am pulling it. Looks like we're going that way. So we are going to go here. And I notice that my scale is about 1,300, which is less than 2,000. So these two, well, those two are equal. This applied force is going to be a lot less. So about half. And I'm going to say FA. And this is the person on the couch. And that is 1, 3, 4, 5 newtons. Again, it is not equal to either of these, so we just leave it blank. The net force, we have F net. We actually have a number here. 2,000 minus 2,000 equals 0. So you're going to have F net. We have 1, 3, 4, 5 newtons to the right. And then my impact of motion, we are going to accelerate to the right because we are unbalanced. All right, so now we have a reminder to go through your zones on the bowling ball activity. Remember what we did with the no touch zone. remember what we had to do when we moved forward, what we had to do to stop, and what we had to do to change directions. Where did we have to hit the ball to make those things happen? You definitely need to review gravitational force and mass handouts, especially the planet questions. Those are going to be big because there's a whole page on the test coming up about different gravitational forces. And remember, acceleration due to gravity has a different notation or a different term that we use when we're talking about objects in space. Please be able to use F equals ma and W equals mg. Okay? Where W is weight, G is gravity. The acceleration due to gravity on Earth is 10 meters per second squared. That's just your constant. A man pushes a 50 kilogram box at a constant velocity. My mass is 50 kilograms. He applies 900 newtons of force to the left. So F equals 900 newtons. Draw a force diagram for the box. So here's my box. My force of gravity. Oh, I lied. My force of gravity, we have to calculate that. F equals m times A. So we have 50 kilograms times 10 meters per second squared. That's going to get us 500 newtons. So downward force of gravity is 500 newtons, and that is dealt by the Earth on the box. My upward force is also going to be equal, 500 newtons. It is my normal force, and that would be on the floor by the box. We are not done yet because we have 900 to the left. So 900 is bigger than 500, so my vector has to be a little bit longer. That is FA for applied force. And that is the person doing the force and the box feeling the force. And that is a quantity of 900 newtons. So the value of the force of gravity here, so this is the force of gravity, not acceleration due to gravity. So that is F equals m times A, 50 kilograms times 10, and that is, again, 500 newtons. I could have also said, hey, see what I just did up there? So there is a reminder here. What is the value of the frictional force? We don't have a frictional force up there. So let me reread the question. Draw a force diagram for the box. That's not the one I want. A man pushes a box at a constant velocity. If I see the words constant velocity, that means that it has an opposite and equal effect. So if this is 900, my force of friction has to be 900 to balance it out, to keep it at a constant velocity. So there's my force of friction. And again, that's on the floor, and the box is feeling that friction. So the value of the frictional force is 900 newtons. The value of the normal force is 500 newtons, because that has to balance gravity. What is the difference between mass and weight? Mass is how much stuff is in an object, and mass never changes. whereas weight is affected by gravity. So, for example, on Earth, our weight is, we'll say, 400 newtons. If we go to the moon, it's going to be about 200 newtons. Okay, it's going to be a little more than that, but not much. The point is, you are going to have less gravitational force on the moon. If you went to Jupiter, your weight would increase because you have a larger gravity. A newton is a measure of force. And inside of a newton is a kilogram meter per second squared. Because again, it's mass times acceleration. An object has a mass of 18 kilograms. What is the gravitational force? So we're looking for force. And we know acceleration on Earth is 10 meters per second squared. So what we do is F equals M times A, 18 kilograms times 10 meters per second squared is 180 newtons. Flipping that over. Here's that funny word for acceleration. This is another way to say acceleration. Okay. So the acceleration on the moon is 1.63 newtons per kilogram. And if a rock on the moon weighs 700 newtons, and remember, weight can be used with you can either abbreviate it with a W or you can say it's force. Either way, it's the same thing. So force, and if you want, you can do a little weight there, 7,000 newtons. How much does the same rock weigh on Earth? So this is going to be a two-step problem. First, we have to find the mass. We don't know the mass because we got to get the mass of the rock on the moon. So M equals, let me get my triangle up here. And if I cover up the M, I am left with F over A. So M equals F over A. So I go 7,000 newtons over 1.63 newtons per kilogram. You're going to notice that newtons cancel. And then I get my calculator. And then I go 7,000, divide that by 1.63. So I should get about 4294. And if we were rounding to 0.5, and the only units I have left over are kilograms. We are not done yet because that is the mass on the moon. We can use the mass on the moon to find the weight on Earth. And remember, weight is the same thing as force. So force on Earth equals, plug this up, M times A. We have our mass. Remember, mass never changes. So even if it's on the moon, it's going to be the same mass on Earth. And we're going to multiply that by Earth's gravity. So if you needed a calculator, times that by 10, 42944. newtons on Earth. Okay. Newton's first law. An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a force. That's the actual law. And then two examples would be like an object sitting still. Let's see. I can't write apparently. And an object at a constant velocity. They're all going to stay the same unless you add a force to them. So, Newton's second law examples, we did a lot of calculations. Again, F equals ma. So, second law, it's you have to use more force to accelerate a heavier mass. That's one big one. If you want to move it faster, you have to push it twice as hard. Or accelerate faster, push 2 times harder. Okay. Again, we have a couple of two-step problems. Imagine you have a rock on Earth with a weight or force of 72 newtons. And we are on Earth, so that means my acceleration is 10. We need to find our mass. M equals, if I go back up here, cover up my M, it is F over A. My force is 72 newtons over 10 meters per second squared. 72 divided by 10 is 7.2 kilograms. So the mass of that rock is 7.2 kilograms. 17 is a bit of a trick question. Remember, mass never changes. So it's going to be 7.2 kilograms. Okay, now the rock is on Mars. Find the new weight of the rock. Well, we know our mass is 7.2 kilograms. And then I'm going to use my chart to find my acceleration for Mars. So I'm going to go over here. It is 3.77 meters per second squared. And we need to find the weight or the force. So again, force is mass times acceleration, 7.2 kilograms, times 3.77 meters per second squared. 7.2 times 3.77. It's going to get me about 27.1. And my units on that are newtons. Okay. The unit for acceleration, meters per second squared, or you can have gravitational field strength, which is a Newton per kilogram. A Newton is force or weight. kilogram measures mass. Weight is going to be in newtons. Gravity is going to be meters per second squared, or newtons per kilogram. Gravitational field strength, again, is the same thing as acceleration, or um, newtons per kilogram. And I just lied to you guys. This is not supposed to be there. I was reading ahead. So gravity should just be the same as acceleration. So gravity should just be meters per second squared. However, it's not really wrong to have newtons per kilogram there. It's all good. Last question. F equals ma, W equals mg, where this is weight. The mass of the pen is 5 grams. Find the force of this pen on Earth. So mass equals 5 grams. We have some shenanigans here. We need to convert to kilograms. And you do that by so that becomes, let's see, we've got 5, and I've got to move that decimal place over 1, 2, 3 zeros. So it's 0.005 kilograms. F equals m times a. So 0.005 kilograms times 10. We are going to make that 0.05 newtons. Okay, determine the tension in each cable. We got to convert those into kilograms. So 3 grams into kilograms, we've got to divide it. So we start with 3, and then we divide by 1, 2, 3. So it's 0.003 kilograms. All right, so we have a ball that is 3 grams, and we have to convert that into kilograms. So what I did up here is 3 grams into kilograms. You have to divide by 1,000. 1,000 has 3 zeros. So you need to move the decimal 3 places to the left. 1, 2, 3. So your mass in kilograms is 0.003 kilograms. We have to find our force. If this is for A and this one is B, A's ball, you're going to have 0.003 kilograms. And you're going to have F equals m times A. So 0.003 kilograms times 10 meters per second squared is 0.03 newtons. So this has 0.03 newtons of gravity, and that is on the ball by the, let's see, cable. I'm going to put C for cable. Actually, this is E for Earth, and then up is C for cable. So this is FT, 0.03 newtons, and this is cable on the ball Those two are equal and opposite, and this is for A. For B, we have the same ball. So we have that same ball being pulled down, and I'm going to make sure that these two are the same length because it's 0.03 newtons. That is your force of gravity, and that is the earth on the ball. And again, this is ball B. Ball B has two strings going up. So that means I have to have two forces going up. And I'm going to go two forces that need to add up to be this length. So this length needs to add up to this length. These two should be the same. This one will be different. So we have FT1 is the string 1 on the ball. This one is FT2, which is string 2 on the ball. And they both are whatever 0.03 is divided by 2. 0.03 divided that by 2 is 0.015. 0.015 newtons. 0.015 newtons. Because these two are splitting everything in half. This one, we have the tension, but we don't know the mass. We don't know. But we do know if its acceleration is 10 meters per second squared. And my force of tension is 726 newtons. And I am looking for F. Song of the day, Delinda. M equals F A. And this is 726 newtons over 10 meters per second squared. And then it should get you about 72.6 kilograms. Okay, now we're going to do this guy. All right, so what is a force, you say? A force is a push or a pull. A push or a pull.
What up, nerds? Oh, man. I can say that because I'm a nerd too.
Don't forget, I have recording in process, so hang tight. How do we represent a force? We do that with a force diagram or a free body diagram, FBD. What do we mean by an unbalanced force? We mean that a force is going to be greater or less on one side or the other, which means it will accelerate in the direction of the bigger vector. If you have an unbalanced force on the system, again, it's going to accelerate at a greater rate. It's going to accelerate. How is an unbalanced force related to uniform motion? It will accelerate at a constant rate. How is an unbalanced force related to being at rest? Well, if you have an unbalanced force, the object is not going to be at rest. And how is an unbalanced force related to speeding up? Again, it's going to accelerate in the direction that it is unbalanced. So right now, top and bottom are balanced. To the right, it is unbalanced. So the object is going to speed up to the right or slow down to the left, depending on where the force is. And again, if it is slowing down, say the object is moving to the right, if we hit it to the left, it's going to slow down. A field is a region around a body that experiences a gravitational force, and a field makes an object accelerate in the direction to the center of the planet or a main object. I would go back and study your old worksheets. Don't use this as the end all be all. You should make note cards. You should quiz your friends. You should practice some calculations. Be able to use your formula triangle and take time to think things through.